Hello everybody. Hello Coach Reza. Hope you're doing great. Uh, so let's talk about assignment 3 and what the expectation from the assignment is. So as we look at the question, we have John Hughes who wants to leverage the leukemia remission dataset. This is the dataset and thinks that maybe a neural network model would be a good choice. So we have some details about the dataset. We have 6 independent variables and we have one dependent variable, that is remission, and just a brief knowledge about what remission is. So as you know, this is one of the biggest examples where neural networks have helped mankind a lot. I think it's important that we know what remission is. I just had a brief reading about it, but I found that it's really great that we have neural networks help us in this domain. So for somebody who has cancer and they are recovering, or they think they are recovering, there are certain tests that the doctors perform, and based on the readings that the test outputs, the remission is diagnosed, whether the patient is in remission or not. So if the patient is in remission, that's a good sign. If he's not, then unfortunately the cancer is still there. And if the patient is showing remission for about 5 years, then the doctor may conclude that the patient has recovered from cancer. So just a brief about what remission is. Stay safe everybody, cancer is not good. And just let's understand what else the question shows us. So there have been previous modeling algorithms used for this dataset, and was logistical regression, and as we see, these scores aren't very good. In fact, they're not good at all. The precision is below 50%, and the F1 score for predicting that the patient is in remission is less than 50%. That means the model is not doing very well. Anyway, we will get into the comparison between this and the neural network in some time, but we have also been given the parameters that we need to use for the neural network to design our network, and how we need to split the dataset into a train and test. So let's move to the code. So as always, first we import the required dataset. We have pandas, we have numpy for properly making datasets, data frames, and manipulating the data that we have. We have pyplot, so that we can plot the graphs and the charts, and that's it. And we first load the dataset, and as you see, I have included it here. That means Colab can understand that this is the dataset, and we have prints the head, that is the first 5 rows of the dataset. Here what I'm doing is, instead of the 0 and 1, I have renamed it to no and yes as labels. So for us, once the classification is done, it is easier to understand with a yes or no rather than a 0 or 1. This is a completely optional step, but I thought, let's try. And when outputting this looks easier on the eye to comprehend rather than a 0 or 1. Moving to see the key statistics for this dataset. So we have key statistics for all the 6 independent variables: cell, smear, infill, Li, blast, and temperature. So the first stat is 27 records. So one of the main things is the dataset only has 27 records. So we'll get to understand what I mean when I say that this is not enough data, but it's okay. We have 27 records for each of the columns, and also for the dependent variable, of course. And for cell, see, the mean is 0.8814, standard deviation is 0.186, which means there is some spread from the mean, but it's not a lot. The min is 0.2, max is 1. And how the data ranges from the first quartile is, so from the min to the first quartile it's a big jump, and then it doesn't increase a lot. So that means there shouldn't be a big skew, but the data is not evenly spread between across the mean. It's not evenly spread. There's a lot towards the left. Then we have smear. So here the mean is 0.63, standard deviation is 0.21, which is a good percentage of this. That means there is a good spread, but we see that the data is evenly spread. Even though the spread is more than this, there is some evenness, so there doesn't appear to be any skew in this data. Similarly, we have we can interpret the skew and the way the data may look for the other columns as well. Moving on to the next step is where we split the data between x and y, basically our independent variables and our dependent variable. So what we do is, from the complete data frame, which has all of the columns, we drop the remission column, so we have all the independent variables into one data frame, which is then converted to a numpy array and assigned to x. Similarly, only the column remission from this dataset, from our dataset df, is taken, converted to a numpy array and put into y. From now we split x and y into train and test. So as we know, all machine learning models need to be trained, and then for us to know whether the model is performing well, we have some portion of the data as test data. So we test the model's performance on this data. So from scikitlearn model selection, we import a function called train test split, and what we do is we pass x and y that we initialized here, and we say that test size is 0.2. that means the testing data will be 20% of the entire data. Random state 100 means it will the sampling for choosing between train and test will be in accordance with the number that has been passed here. This helps if there are multiple developers working on the same model. If they have the same number here, it would say to the machine that sample using this number, so everybody has similar samples. It's not different for every developer. And stratify y means the way the sampling will happen. We will have test data which includes data from all the different classes that are present in evenness. Moving on to the next block, this is scaling the data. As we know that using machine learning models with very large numbers reduce the performance of the model, so it's always good to scale the values that we have. It's always better to scale the values down between maybe -1 and 1, so that the machine can easily solve with these numbers. It can easily perform functions on these numbers and work faster. So this is how we do the scaling. Now this is one of the major parts of what we are trying to do here. Script for neural network. So we first import the class called MLPClassifier, and we make an object of the MLPClassifier with the parameters that we want. So hidden layer sizes. So as we know, machine learning models or let me say deep learning or just a second, neural network models have an input layer, a hidden layer, and basically some hidden layers and the output layer. So what happens is the inputs are given to the model, some weights are multiplied to the inputs, a bias is added to it, an activation function is applied on it. This basically this non-linearates the model. If we remove the activation, what we would get is even if we have like 100 hidden layers, still the output is going to be a straight line, or basically your model would always be a straight line. With this, with the activation function, what we can include is maybe a sigmoid function, maybe a tan h, or nowadays what's popular is the ReLU function, or there's one more, anyway, this non-linearates or adds non-linearity to the model. So if the data that we have can't be classified using a line, a straight line, and maybe it can be classified using a curve, then we can use an appropriate activation function, and that makes our neural network robust. And then the output is given. The output will obviously have a classification done, and the way the neural network model learns is every time there is data given. So basically let's go to the code and understand the params. So hidden layer sizes 642 means there will be 3 hidden layers, and basically the first hidden layer will have 6 neurons, second one will have 4 neurons, and the third one will have 2 neurons. After that will be the output node or the output neuron. The function activation ReLU is nothing but, as I said, a non-linear function which is applied to the neural network, so that if our data can't be classified using a straight line, ReLU is going to help dictate a particular curved splitting of the data so that it can classify on the graph. Max iter is the maximum iterations or the number of epochs that we want this neural network to do. So coming back to the diagram, so every time we give an input to the neural network model, it comes back. So basically the data will move this way through the hidden layers, and it will activate the neurons based on the activation function. So what happens is we give an input, it is multiplied with the weight, and bias is added, and the activation function is applied. If there is positive activation, a particular neuron will be activated. Then it will communicate with another function. Again, it will check whether there is activation or no, and then communicate further. This is called forward propagation of the input, and this is where the classification occurs, and this is the output. So every time the model checks with the trained data whether its output is right. If it's right, then there may not be any back propagation. But if there is some discrepancy in the output, there will be back propagation, and the layers, the weights of weights multiplied to the inputs will be adjusted by itself automatically, and this cycle is one epoch. So if we have 10,000 epochs, then there will be 10,000 forward propagations and backward propagations. So our model learns more. So that's how this works, and that is what we say when we say 10,000 max iter. That means we want 10,000 epochs, and the model will learn 10,000 times using the same data. Solver Adam is nothing but the function that the neural network uses to basically solve or go about itself. So if we check what else we have as solver functions, we would come to know that we have something called as, so solver Adam is the default, and we have solver LBFGS and sigmoid, stochastic gradient descent. So this is the type of method that we want the neural network to use to train itself and perform well. So we have used Adam here, and so I will remove what we added here, and again random state 100 is the same as the random state that was explained here. The sampling will happen in that manner. Then we have trained the model using the fit function. The scale data and the y train has been fed to the object, our MLPClassifier object, and we have the prediction here. So it's time to see how well our model has predicted. So since we have only 27 records and we have like only 20% of the 27 as testing data, unfortunately we only have 6 records that are being predicted here, and they are the testing data that we have. So df2 is okay, so this is where I have just made a small table to understand how well our model is performing. So where it is actually no, our model has predicted correct. No, here it should have been yes, but our model says it's no. Here it has to be yes, our model says correctly yes. Here it's no, our model says yes. This is again a mistake. No, correct, no, that's right. And when we go ahead and see how well our model is actually doing, we have certain metrics for it. So what we've printed first is the confusion matrix. Confusion matrix is nothing but the true positives and the true negatives, false negative and false positive. So based on this, we have the classification report, and this is the precision, which we can see is greater than the logistic regression. The recall is also greater, and the F1 score is greater, and the precision recall and F1 score for yes is it's not greater, but it's okay. Oh, it is greater. It is greater. So our model has actually done better than the logistic regression. Just a brief about what precision is, what recall is, and what F1 score is. So precision is, as Coach Reza says, how many dogs that, suppose we classify between cats and dogs, how many dogs that our model how many dogs that our model says are dogs are actually dogs. So out of what our model says, suppose it says 5 dogs, and out of that we have 4 really dogs and 1 cat, that means 4 by 5 is the precision. That means it is 0.8. What's recall is, out of all the dogs that we have fed to the system, if our model can predict out of 10 maybe 8 right, the recall would be 0.8. And the F1 score is a weighted average between precision and recall. So the thing is, we can't rely on only precision or only recall, and a good model will have both of these metrics as good figures, and hence the F1 score will also be good. What would happen is, suppose we have a scenario where there are maybe 9 dogs and 1 cat, and our model says all are dogs. That means the accuracy of our model will be 90%, which is actually wrong, which is actually not the best metric, since there was only 1 cat and our model couldn't predict it. So that is why we have precision and recall for each of our labels, and the precision and recall both should be decent figures for us to conclude that the model is doing well. So our model is not the best model, but we have our own reasons for it. Neural networks generally needs a lot of data for it to train and understand itself, but here we have only 27 records, out of which only 21 are training records. So our model has still done decent for the 27 records or 21 records. In contrast, I've also done the logistic regression, which is also mentioned in the question, and the logistic regression, it doesn't perform as well as the neural network. So how can we improve the neural network is by my first suggestion would be to increase the number of records that we are feeding the neural network to train itself. So maybe more data is required, so the efficiency or the performance of the model will increase. Second could be increasing the number of hidden layers, because the hidden layers are very important when it comes to backpropagation and training and understanding the model, or understanding that the model is doing wrong, or how much the model is doing wrong. So it can train itself better if there were more hidden layers. And the third would be adding the number of iterations. So if we have more epochs, so epochs are basically the number of back propagations is directly proportional to the number of epochs. So every time a complete iteration or an epoch occurs is when the model learns and understands from its mistake and changes the weights assigned to each of the inputs. So these are the suggestions how we can improve the model. Hope you like this video. Thank you very much. Bye.